do presentation for Project RAC, which is our rocket analysis tool, and Esther.
Omar.
I'm Maison project.
And just a presentation outline, I'll be going over the motivation, context, and background, the problem statement, statement of your own goal, as well as the validation outline. Omar will be talking about our structural subsystem fall results, and Mason will be talking about our electrical subsystem fall results, as well as our current schedule plan for winter and spring, as well as our budget and resources, and wrapping up our presentation. So the motivation for this, to build a rocket test stand comes from the AIAA UH chapter. So that they want to build their own rocket engines. So when the current practice right now is to buy their rocket engines, but this comes with set limitations on data. So Team 13 will provide a rocket test stand that provides data such as our force versus time curve, and as well as calculate the impulse on it and the maximum thrust. This rocket test stand will be able to go up to an O-class motor, and an O-class motor is just how they classify rocket engines based on the impulse, which is about 41,000 newton seconds. And so the last section here just covers the two main components, that the structural subsystem and the electrical subsystem, that Mason and Omar will be talking about in more detail. So for our problem statement, one of the key points that I wanted to highlight was that our major constraints are the cost, the transportability, as well as the ease of assembly, and we'll be going in more detail how we plan to address these. So our statement of year-long goal, what we'll be doing for this academic year is we'll be drafting our rocket test stand for our structural subsystem and performing FEA on it, and for our electrical subsystem, we'll be designing and creating our circuit to provide that data. And the last component is that we'll provide instructions for how to use and the specifications for our rocket test stand. So for our validation outline, the three major components are the structural integrity, the electrical subsystem, and the final assembly. So for the structural integrity, we'll be testing the rocket test stand through FEA, and we'll also do static loading on it. And for our support system, which is our concrete, that will be revised by a civil advisor. And for our electrical subsystem, what we'll be doing is that to ensure that the data is outputted correctly, we'll test it on smaller motors, which are C-class motors, which are less expensive. And the final assembly will also, once it's all integrated, we'll make sure that that is holding structurally, as well as test the higher powered motors and make sure that those are providing the correct data for our electrical system. And now Omar will talk about our results for our structural subsystem.
Thanks, Esther. So this is the first design we came up with. We had a change of the client halfway through the semester. This was for a horizontal design for testing. And then we conducted a design matrix where we compared the three major ways local universities and organizations usually test rocket motors. That's a horizontal, vertical, upwards. So the rocket is flying upwards, and then vertical, downwards. We talked with our client, AIAA, to see the major criteria they're looking for. And the two major ones, obviously, were the real flight simulation, so how accurately the testing aligns or models the actual flight, as well as hybrid testing, since this is where they're looking to move forward with their rocket design. So for vertically upwards, it was 5 out of 5 compared to the downwards and horizontal, since a rocket flies upwards and plays a role in the pressures inside the hybrid engine and the forces that are also at play with the simulation. We started with a nice drawing, so we wouldn't have to CAD, and then the client finds some inconsistencies or things they disagree with, and we have to recad. So we drew everything out. It turns out that it's going to be about 2 meters long. We have a front view, a top view. Top view, you can see the strain gauge right there, the pressure sensor. And then we drew a 3D picture as well, looked at local resources we can find, and these are the pictures here of references of how we came up with our ideas. The 5 main challenges we had were vertically controlling the engine, horizontally controlling the engine, anchoring the whole test stand to the ground. The main body that deals with the majority of the force and the stress of the thrust, and then the safety. They were fun to tackle these challenges. We came up with innovative ways to manage them. It's a lot to talk about, but for the sake of the 12 minutes, we'll just have a brief overview. For the vertical control, we have 2 steel bars right down here, and then a 0.25 inch slab. Everything's made of 304 stainless steel. For horizontal control, we have the threaded rods that are holding it together, and the reason we chose threaded rods is because you can change the diameter of them, and hence the test stand will work for a variety of different engines. The main body, 4 by 4 inch box tubes with a 0.25 inch thickness, and after doing the FEA, it is the optimal with regards to cost and managing the stress. It's the optimal design we agreed upon. And then anchoring, we went to the civil department. We were like, okay, we have an issue with that. They recommended a certain concrete that we can use, and with 2% steel as reinforcement. And then they also told us how we can manage to anchor the test stand to that concrete using a red head anchor. We're looking to do more analysis in that. That was just word of just relying on the professors telling us what we'd be able to do. I believe it was Dr. Mina from the civil department. Hopefully we'll have a stress analysis on that through SolidWorks. And then with safety, we talked to our client. They proposed using a mesh, steel mesh, around the test stand so that if, in case of an explosion, you have something catching the debris. This is a closer look on all our different designs to overcome these challenges. Over here you see the rails, and you have a pulley system for ease of maneuverability for the rocket. So you can put it, it's 2 meters long, so you put the engine, you pull, it slides on the rails, and then it's held up by these 2 steel rods. The engine is looking to be 50, 60 pounds, so that should be able to handle the stress. And then you have here for the horizontal control, you can put the thread rods right there so you can manage to hold it upright. And then the FE analysis. The rocket was looking to be 4,600 newtons. We almost double that for our analysis, making it 8,900 newtons. And with that, it's still very high factor of safety, 10.83. So 304 stainless steel looks to be very reliable. And then Mason's gonna go over our schematic of the circuit.
All right, so yes, the second subsystem of Project RAT is going to be our electrical circuit subsystem. This is going to be the system responsible for obtaining all the data, and I'll have our sensor systems for the maximum thrust, force over time curve, and also the temperature at the nozzle. We have a block diagram outlined here at the pink boxes. That's going to give us an overall idea of the components that are going to be needed to complete the sensor system. In the black box at the bottom left, you're going to see our load cell that we've already identified on the left-hand side, and the wiring going to the HX711, which is going to be the amplifier that we identified that is designed specifically for load cell sensors. It's important to actually amplify the signal output from the load cell of millivolts to voltage so that we are able to accurately read the change in resistance from that load cell. It is then going to be wired to the Arduino Uno, which is going to be recording our data for later analysis. So this is going to be our Gantt chart for the fall of 2018. The pink line is going to outline where we currently are to date. To the right of that are going to be the remaining tasks that we need to carry out in order to complete the overall milestone of the design drafting. So as Omar said, we already conducted the FEA on our structure. We are just awaiting the final review from our faculty advisor. And then on the captures of the circuit schematic, we have already completed the load cell circuit schematic. And then when we identify our new temperature sensor, we are going to complete the schematic for that as well. For the remaining of fall 2018, since we did the mid-semester change the orientation of our test stand and design, as Omar said, we are going to complete the system analysis of our anchoring system. We are going to identify a new temperature sensor solution, order electrical components so that they can be here by early spring semester, and then create a bill of material for our new sponsor that was identified through AIAA so they can order any additional material that we need. In the winter of 2018, we're going to attempt to get a head start on the fabrication process of the structural subsystem. Some of the supplies or materials are on hand at the workspace of DaVinci Labs, where we'll be fabricating the structural subsystem that will be beginning over the winter break. So the plan for the spring of 2019 is going to be starting the fabrication and the completion of both the structural and electrical subsystem, and then integrating those subsystems to create the final product, which is Project RAT. And then we will actually be conducting our final testing after the C-class motors of the N-class motor to make sure that it's properly obtaining all the critical design criteria, such as the force versus time curve, temperature at the nozzle, and the maximum thrust. After successful completion of the testing of the N-class motor, we will then present the final product to the AIAA team. On the left-hand side, this is going to be our itemized list for the our materials needed for the Project RAT. In bolded out are going to be the materials that we will be responsible for, which are going to be the main components for our electrical subsystem and our anchoring system, such as the load cell sensor, the temperature sensor, the pulley system, and our anchoring system. We have identified the majority of the resources needed to execute Project RAT. The one being DaVinci Labs, which was identified through AIAA. They will be the ones providing the structural material with 304 stainless steel. In addition to that, they will be a great resource since they've already assisted in building other rocket test stands. They will also be helping with the fabrication and the welding of the structural subsystem and be able to assist in the FEA review as well. The AIAA electrical engineering team will be assisting in the coding and implementation of the electrical subsystem. And then we've also identified the final testing location, which is located in Angleton, Texas, where we already have permission to put down the anchoring system with concrete, as Omar stated earlier. The resources still needed. Again, since we got a change of sponsor midway through the semester, they're going to want to measure the temperature at the nozzle of an O-class motor, which is higher than originally anticipated at 3,200 degrees Celsius. So we're finalizing finding a sensor that can withstand temperatures of that magnitude. So in conclusion, a little overview of the key takeaways of what we've done this semester. We will be building a test rocket stand for AIAA to give them the information that is needed to build their future rockets. A new sponsor. The new sponsor is going to again be a great mentor in actually building and executing this test stand. Our final design is already drafted using SolidWorks, and we have conducted our FEA analysis. Again, the final step in that is actually having a faculty advisor review it. We have completed the load cell circuit schematic, and moving forward for the winter and spring, we are going to complete the fabrication of the structural and electrical subsystem, integrate to create Project RAT, perform the final testing, and have our final presentation to AIAA. That's going to conclude our design review, and I'd like to open up this time for any questions.